Today we will get started with routers, and then we will learn about the types of addresses, logical addresses, and physical addresses. We will learn about the different networking models, OSI models versus TCP IP, and we will finally learn about data encapsulation. The routers, first of all, they break both the broadcast domain and the collision domain. And that's the big difference between routers and switches. Switches, they break the collision domain, but they don't break the broadcast domain. It is the same as the broadcast domain in hubs. But routers, they break the two. Each port in the router represents a new network. And then in order for two computers in different networks to communicate, they have to send a request to the router and specify the destination network address. So not only computers having their own proper addresses, but even the network has its own specific address. And we will talk about the types of addresses and how they work in details in a minute. So there is no such thing as a broadcast request to another network. And this is really useful in that it limits broadcast messages and it increases the bandwidth. So for example, in the internet, where you have huge number of networks connected with each other, you don't want anyone to be sending a broadcast message that will flood the internet and it will be broadcasted to everyone in the internet. That would be very bad, and you are making networking devices waste a huge bandwidth in things that are not necessary. Let's say, for example, I have two networks. Each network represents a different department. For example, let's say that this is the Department of Finance in just one single huge company. This is the Department of Finance. And let's say that this represents the Department of Human Resources. And the Department of Finance, we have some number of computers. We have 3 computers, and they are all connected with a switch. Essentially, you don't want to mix networks and you don't want to mix departments. So you don't want them to be all in the same network. That's why you need to separate them. And that's why we use a router. So switches, they don't break networks. They don't define networks. Routers define networks for each port. So for each port connecting to the router, we get a new network. In this case, we have 2 ports activated, which means we have 2 networks, network A and network B. So if I have, for example, someone who loves shouting, when he sends a broadcast message, as we said, the switch, he doesn't break the broadcast domain. So this blue area represents the broadcast domain. So it will be forwarded to the rest, to every port. And it will be also forwarded to the router. But it stops here. So broadcast messages, they don't go to the other network, which is network B. And it makes sense. Because first of all, you will make the bandwidth, you will increase the bandwidth for both networks by limiting the number of broadcasts. As for the collision domain, the router also breaks collision domain just as the switch breaks the collision domain. So far, we have been using the word addresses, but without actually knowing what they are and how do they work. The first thing that you need to understand about addresses is that there are actually 2 types of addresses. There are physical addresses and there are logical addresses. And we will explain the difference between the two and why they are required. First of all, physical addresses. So physical addresses are just addresses that are embedded by the computer manufacturer to give a unique ID to that computer. So each computer that exists today has its own unique identifier called the MAC address, also known as physical address. But trying to communicate using only physical addresses is really hard in large networks. That's because the networking devices should be able to remember the list of all the addresses that exist in the world. And that's a lot. That's because you have each networking device trying to remember billions of addresses. So using physical addresses to communicate is only a good option in local area networks, such as this network right here, network B or network A. So in this local area network, we only have 3 computers. So the switch should only remember the 3 addresses. That's because a local area network is by definition a network that is small. It's not really huge, such as the internet, where you have millions of networks trying to connect with each other. The second drawback of using physical addresses is that, let's say in this department, the human resources department, they were using really old hardware. They were using old computers. So they decide to replace these computers with new ones. So we have computer G and H. Let's say that F was down. It just simply was broken. And they get another computer called I. Now the list of all the available addresses need to be updated everywhere. In here, in here, in here, and God knows how many networks this router is connecting. It could connect millions of other networks. For example, the IT department, it could even connect to another router that connects to another network, and so on and so forth. So it needs to be updated everywhere, and that's really not scalable at all. And so what they did is that they said, why not for each computer should have its own logical address. Logical address are just generated by computers. So each computer should have 2 addresses, a MAC address and a logical address. But in order for computers to communicate over networks, they need to specify the network address. So even the network should have its own address. And the second thing that is really important is the separation of responsibilities. So the router needs to only remember the network addresses that are connected to each port. So each port represents a new network. And as we said, for each network, it should have its own address. And of course, it would be logical, since a network is just multiple computers trying to communicate together. So you cannot put a physical address in that network. And so we have network A has address N1 and network B has address N2. And then let's say that D wants to send message to C. He knows the address of C. It exists within this network N1. So he specifies send a message to the logical address C of the computer C that is located in N1. The switch, once he knows that this exists in a different network, he automatically forwards that message to the router. So the router knows which network this message should be forwarded to, and he forwards it to this port. And then the switch would know which computer should get the message. And then, for example, tomorrow in the finance department, this computer gets broken and it is being replaced by another computer, G, for example. You can use the same logical address that this computer was using without breaking communication. So D doesn't need to know that there is another computer that was replaced. So he doesn't need to worry about the physical address of the new computer. And this is scalable because, first of all, we have separation of responsibilities and we have more flexibility. Logical addresses, are also called IP addresses, are composed of 4 bytes, which means 32 bits, since each byte is 8 bits. And physical addresses, or MAC addresses, range from 6 bytes to 8 bytes, which means from 48 bits to 64 bits. The reason they made IP addresses 4 bytes, it's because they thought that 2 to the power of 32 would be more than enough to represent all devices. Since each bit could hold either 0 or 1, then we got 2 to the power of 32, which would be 4 billion addresses. And they thought that they could represent all the network addresses and also all the devices within those networks using 4 billion addresses. But they were wrong, and that's why they created another version of IP called IPv6. So this one that we will study and focus today is called IPv4, but just keep in mind that there's another version called IPv6 and it has 16 bytes, which means 128 bits. And that would be really more than enough. This is an example of an IP address. We have 32 bits and it is in binary. But working with IP addresses in binary would be really hard. The first thing we would do is that we would separate each byte by a dot. So we count 8 bits and then type in a dot. We separate each byte by a dot. That's because we want to make it easier for us to make a delineation between the network address and the host address. You see, the way we give addresses to networks and computers within those networks is exactly the same as we do when we try to give an address to streets and houses within those streets. So each street have a specific address, and in order to give an address for a house, you need to first specify which street it belongs to. Similarly, I can say that the first byte will represent the network address, and then all of the rest 3 bytes will represent computers within that address. Or I can say the first 2 bytes will represent the network address, and the second 2 bytes will represent the host's addresses. So we want to make it even easier for us and transform each byte individually to decimal. So we would have something like this: 192, that's 168, that's 5, that's 4, something like this. This is way much more easier to work with than working in pure binary. And the way I like to transform a byte from binary to decimal is by first drawing a byte like this. So I have 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So I have my byte. So this is the 0th bit, and this is the 7th bit, and therefore I have 8 total bits. And what I would do, I would say, if I set this bit and change it from 0 to 1, and the rest would still be 0, what would be the decimal representation of my byte? That would be 2 to the power of 0, and that would be 1. And I do the same thing for the rest. So if I set this first bit from 0 to 1 and the rest would all be 0, I would have 2 to the power of 1. That would be 2. And so on and so forth. So 2 to the power of 2, that would be 4. And then 2 to the power of 3, that would be 8. 2 to the power of 4, that would be 16. 2 to the power of 5, that would be 32. And 2 to the power of 6, 64. 2 to the power of 7, 128. So if I have a byte like this, I would go to this tiny table right here. So I would add 32. I would add 32 with the first bit, that would be this one, 32 plus 2. So that would give me 34. And then dot and I have the 1, 2, 3, 4, 5. So I have the fifth bit, which is 16 plus 32. That would give me 48. So I have 48, and then I have this byte right here, but I have only the first bit set. So that would be just 1. That's 1. And then this one right here, where I have the last 5 bits. So I would add 8 plus 16 plus 32 plus 64 plus 128. And that would give me 248. So as you can see, if I set all these bits to 1, that would give me the maximum value for a byte, and that would be 255. So this is an easier way to convert any address in its binary form to its decimal representation. You first separate each byte by a dot. You draw this table if you want, which is a cool method, and then you represent each byte in its decimal form individually. We have 5 types of addresses in IPv4. We have type A, B, C, D, and E, but we will only focus on the first 3. The rest are out of the scope of today's lesson. The difference between these addresses is in their first bit. So the first bits always start in type A addresses with 0, and type B starts with 10, and type C with 110. That's because if you try to make the range and do the decimal representation, you would find that all type A addresses, the first byte would have a decimal value between 1 and 26, and from 128 to 191, and from 192 to 223. There's a reserved address, which is 127. So it is actually from 1 to 127, but 127 is a reserved address for to represent the local machine. So the actual, they made it this way so that when you see any address, just by looking at the first bit, you would already know how big the network is. That's because type A addresses have the first byte reserved to represent the possible networks, and 3 bytes to represent devices. So you have 2 to the power of 8 possible networks and 2 to the power of 24 possible devices per network. And type B, you have 2 bytes reserved for networks, and type C, you have 3 bytes reserved for networks. So what they did is that they did a simple mask. So a mask is just to make it easier to differentiate between the network address and the host address and devices. So the mask of type A addresses, just when I look at any type A address, I would know that the first byte is reserved to represent the network addresses. So I say 255.0.0.0, which means this is the mask. So the mask will make it just easier to make the difference between the bits that represent the network addresses and the host bits. And then the type B, since I have 2 bytes reserved for networks, then I have a mask of 255.255.0.0, and mask of type C, I have 255.255.255. So if I give you this address, let's say that it represents just a laptop inside a network, and I ask you a question. I say, give me the network address that this device belongs to. The first thing that you would do is that you would go to the first bit, and you notice that it is set to 0, which means it automatically is a type A address. And in type A addresses, we have the first byte reserved to the network address, and the rest of the bytes will represent the possible host that you can have within every single network address. So which means the mask is 255.0.0.0. So this is the network address. My network address is 010000010 dot 0.0.0. So I'm just following the network mask. But I took the first byte as it is because if I follow the mask, it says that you must take the first byte. And then if I turn this into decimal, I see that I have the first bit set, which means 2 to the power of 1, which is 2, and the sixth bit set, which means 2 to the power of 64. If I add them together, I get the decimal representation of my network address, which would be 64 plus 2, and that would be 66. And as we said, type A addresses must range from 0 to 126. So the network address is 66.0.0.0. So in this case, my 66th network could have 2 to the power of 24 minus 2. Minus 2, that's because the last address will be reserved for the broadcast address, and the first address, which is this one, .0.0.0, is the network address. So we have 2 to the power of 24 hosts within just one network. This network, the 66th network. It's as if I have one street, just one street, but with millions of houses. In the beginning of networking era, it was a little bit hard to make computers from different manufacturers communicate. So one has a way to implement things that is different from the other. There were many tasks that need to be addressed in order to create large-scale performance networks. These tasks could be as low level as setting up cables or as high as trying to create distributed systems. This is why conceptual network modules such as the OSI module or TCP IP were created to separate concerns and organize tasks and set standards. So these are just theoretical models. They are standards of how information should be transferred. So they set the standard, and then manufacturers would try to implement those standards so that we can make it easier for computers from different manufacturers communicate because they are following the standard. The OSI model is divided into 7 layers, but a simpler model of 4 layers is used today, which is the TCP IP model. So before the OSI model, it was pretty much impossible to make computers communicate with each other, especially if the hardware was created by different manufacturers. So if I have, for example, a network, this one network A and this one network B, but network B was created by a different company. So both the switch and the computer was created by another company than this network. And if you try to create an application that should describe how data should be transmitted from the computer to the cable, and from the cable to the switch, and from the switch to the router, this network right here, they would describe their own way of how doing that. It's not necessarily the same. For example, this one, they use 5 different protocols to order the router how he should transfer data from the router to the switch, or from the switch to the computer, and from the computer inside how he should treat that information. And this one, they describe just one protocol that does everything. So trying to make these communicate would be pretty much impossible. So programmers had their own way of describing how should data be treated. But when OSI model came in, and when the TCP IP model came in, they described a set of standards how data should be handled, how data should be forwarded from one machine to another, from one device to another. And so I made this table to make the comparison between the two models, between OSI and TCP/IP. As you can see, in OSI we have 7 layers, and in TCP/IP we have 4 layers, and they are very similar to each other. Just minor differences in that in the TCP/IP we have the application layer, which should represent all of these three, and we have the network access layer that is divided to 2 layers in the OSI model. And in here we have the role for each layer and the protocols that should work on each layer. So this is a layered architecture. And what do I mean by that? I mean that this set of protocols need to use these set of protocols in order for them to work. And these will use these, and so on and so forth until we reach the bottom. So if you have a team that wants to create a networked application, you don't just create whatever you desire. You don't just go in and start creating, for example, as we said previously, one protocol that does everything, that orders how the hypertext should be transferred, and also how the router should transfer data from the switch to the router, and from the router to another router. And so you have this separation of responsibilities. So what you would do, you would